All right, hi everyone. Hope everyone had a good coffee break. So we're going to continue with session two, tools. And presenting first will be Federico from FCI Research Center in Germany. I believe he is on there, so please go ahead and share the screen and we'll get started. As a reminder, it'll be 5 minutes per talk, and then we'll have the 20-minute group discussions followed by the 20-minute panel discussion. Whenever you're ready, you can go ahead.
Yes. Hi. Can you hear me well? Can you see my screen?
Yeah, we can hear you and see you.
Good. Perfect. Thank you very much for having us. Anton, my co-author, is also here in the talk for later for the discussion. And we're going to be presenting our Opera vision, which is an open platform for extensible robust accelerators. So what does all of this mean? And basically, you know probably a lot of these accelerators. There are a lot of them in the literature. These are some of the most known ones, and they all more or less have a similar architecture if we abstract it a little bit. So there is always like some kind of compute element, some DMAs to move data from external memory to internal memory, some controller unit, and so on and so forth. But comparing these accelerators is very complicated. And you all have been in this situation probably. You go to a conference and you get someone that says, oh, my accelerator is smaller. It has a higher throughput. It consumes less energy. It's so good, right? But then if you take a look at the actual numbers in the paper, for example, I occluded the name of this work because I don't want to speak badly of some work. It was a very good work. But if you want to compare your work with a previous accelerator, it's very difficult. Especially, let's look at this example. You have a different technology, different precision, different amount of processing elements, different amount of memory, different frequency. So how can you really say this accelerator is similar or better than this other one? It's pretty difficult to compare. So our vision is to have this kind of tool, Opera, that is composed of a hardware generator framework where you can model your accelerator in an abstract way, export Verilog, system Verilog, and then pass it through all of these tools to actually get to the final tapeout. And this is a vision, but one part of this is already open. I will go very quickly over some of these features. So the hardware generator framework is built around Chisel, and it describes a little bit the structure of the accelerator in this generic manner. The idea is that you can replace part of this and reuse parts from other works, for example, the DMAs, and you can only focus on the execution unit, for example, development. Then we will have verification, of course, because we can change parts of the design. We will put a lot of focus on verification. This will be powered by a library that we will put open source also. That's called chips for sequential equivalence checking. Then we will have unit and integration tests, of course, because there cannot be an open platform without actually verifying that new features that are being developed actually pass the tests. We want to have an AI compiler because all of these works normally compare different networks with different parameters, different input sizes, and so on and so forth. We want to make this more uniform. So we want to integrate also models as benchmarks inside the AI compiler. And we would like to have some kind of integration with tapeout tools. Now, and of course, yes, the design space exploration should be on top of all this to explore different accelerator configurations. Very quickly, what is the current state? So we have open sourced the hardware generator framework. This you can find here, at least the first version. And I will show you very quickly how this looks like. So you have some class that defines your basic computation. It doesn't have to be a matrix multiplication. It can be anything that operates on multiple matrices. And then you build on top of this, you build, for example, your implementation. Let's say your systolic array, which you configure in the middle in some kind of configuration object, and then you instantiate. You can also configure the SRAMs, how they are connected to this computing unit, and so on. But I will say, if you are interested, go to the code and to the paper. We export C headers, for example, for integration with the AI compiler, device tree information for more integration with QEMU, and so on. What are the next steps? So we would like to gather feedback from the community. What other tools do you think could be integrated with this framework? Do you think we need new abstraction layers that we need to develop to be able to model a wider set of accelerators using this kind of hardware generation approach? And what other features would you like to see in Opera? And of course, if you want to collaborate, please reach out. And that's from my side. Thank you very much.
All right. I guess next up, Carl from Northwestern will come and talk to us about hardware REPLs.
Excellent, and I should be sharing. Cool. All right. So I'm here today to posit to you that hardware deserves a REPL. Doing anything with hardware is slow. This is a no-op change that I did in one of my recent projects. 5 minutes later, I got the exact same thing after I literally touched the file. I literally sat there for 5 minutes waiting. But software they will not let themselves suffer with this. They have incremental compilation, they have fast compile times, but they also have interactive tools to work with. They have REPLs, or in the modern day, you have notebooks. You can interactively visualize and graph data, touch data sets, view, do everything you want from within a notebook. Now, why don't we really have this kind of thing for hardware? But before I get anywhere into the why, I want to present a bit of a mock-up that I have been using as a guiding vision for my work. So I hope this isn't too small for everybody here in the audience. You start from a prompt, you run a simulation on something. You let it run, and it fails. But why? You violated an assertion, sure. But now it doesn't stop. It didn't dump your waveform. It didn't end the simulation. It's just waiting for you. It's waiting for you to interact with it. So ask for the history. Get the last couple of clock cycles. All right. There's an interesting -1 here, and then there's the assertion. So let's drill into why that happened. You drill into that. And now you ask for what happened in this clock cycle. What are all of the events that happened? And it tells you, and eventually you see there's an assigned amount remaining is 8 minus 9. It doesn't work. So you find the bug, you found it. Notice there's no need for waveforms, and you have real values. You can actually poke at the circuit. You edit the design in your favorite text editor, you save, you reload, you run, and it finishes. So there's a guiding mock-up. This is what I have been aiming for. So this feeds into a larger vision I have of interactive hardware design environments called Chill, where the language itself is interactive, the same way you have a Python REPL. You do the same for hardware. You can redefine hardware blocks as you're going, their I/O, their components, their internals, and so on. It's a build system where you can add and remove passes, you can explore the design, you can have things run automatically when something in the tree changes. And the most interesting one to me right now, and the one I've been focusing on, is the debugging simulator. This is essentially what you would want out of a waveform debugger, but in a GDB-like fashion with watch points and, most interestingly, time travel. And today, I'll finish off with talking about that part of the work. So debugging a lot of our hardware is really the same as debugging software. We're just building simulators which simulate hardware. That itself is software. We can just reuse all of the same software debugging tools that we've had. And it turns out if you just use the tools we already made for software, you're pretty close to hardware REPLs for at least debugging already. And with time travel, you can even do this with R, or you can even do time travel with RR, which gets you very low like overheads on just being able to collect everything. Now, time travel, you may think that like as we know with waveforms, collecting traces, you can generate enormous amounts of data, like truly exorbitant amounts of data. We found that with RR, even on non-trivial designs, you get traces that are like rounding errors on your disk capacities nowadays, which is great. And these are like full cores running full simulation tests. And the interesting issue we come across is how do you match up names? This is a Verilator generated name from a chisel name. That is exactly what you get. How do you make them match? And there has been some work on this, but it's partial and it does not exactly fit what we need. So if you're interested in working with me or like talking about this more, find me. My go-to avatar is usually Hobbs. You'll find me in Matrix with that. And then all the links and everything are here.
All right, next up, we have a virtual talk from Ethan from Cornell, who will tell us about hardware testing and simulation in Rust.
Yes. Can everyone hear me?
Yep, we hear you. Can you share your screen and start the presentation?
Yes. Can everyone see my screen?
Yep,
Is this text size legible enough?
yes.
Okay.
All right.
So, as introduced, I'm Ethan. I'm studying at Cornell University, and I will show you my simulation front-end / testing tool called Marlin, which allows you to test and do simulation driving from Rust. So, here, just for the purpose of this, I'm going to use a demo because I think that's the best way to illustrate what's going on. Here I have a simple like pipeline tree adder, and I just instantiated it so that it takes in like 4 inputs, and produces an output. So how do we test this, right? Well, we can just create a Rust project. I've already done that here. And then we now have a main.rs. So we can then add the library Marlin, which is just a Rust crate. So we just use whatever you want in Verilog. Just use the standard Rust tooling to add a crate. And now we can import the crate. And now we're ready to use it. So we have our spade design at source / main.spade. And the thing we're testing is called main. So now we just declare that as a struct. And now we have this struct, and this struct has all the ports of our design as Rust struct members, right? So now we can actually create this struct. This is just plumbing that we have to do with this library. So I'll do that quickly. And now we have access to a version, like one instance of the design. So we can just assign in Rust to A, which we get LSP support to. And you notice that it's U8, which is the smallest thing that could represent what we need. So I'll assign this to 1, for instance, and the rest I can also assign to say 2, 3, 4. And this is a pipelined adder, so we will want to get some clock cycles in. So we can just use a standard Rust impl on main. I'm not sure. Yeah, okay. And then let's create a tick function. You will set the clock. You will get our LSP completed clock like that. And then this eval method corresponds to Verilator's eval. We can tick twice because it's a 2-cycle thing. And then we can use standard Rust print on the output port. So if we run this, we'll get actually that's not correct. I would want that to be D, in which case now it's 10. So that is effectively how you would use Marlin to test a Rust project. In this case, we've done it using a binary. But you can also use it using standard Rust tooling like cargo test, and you can write it with tests because it supports like it supports parallel running. And what you should notice is what did not need to happen, which is that we did not need to write a make file. We didn't need to write a custom Python runner. We didn't need to remember what ports are in our design, which maybe we should. But we could get like type level feedback on that. And there's no magic going on here. All of this is vanilla Rust. We just created a cargo project using standard Rust tooling, and we've written normal Rust code. And it's just worked. Um, so that's kind of my goal with this tooling, which is that it should transparently integrate so that you don't have to do any extra effort into testing your hardware. And the other thing to notice is that Spade is not like it is a first class hardware description language, but it does compile to Verilog. But we don't have to look at Verilog at all here. We can just treat Spade as what it is, which is its own HDL. And since this is a very low level kind of binding, you can create more powerful abstractions on top of this. For example, if a language has algebraic data types, Rust also has algebraic data types. So instead of bridging a port on the top level as just an int, you can bridge it as a Rust version of the algebraic data type. Yeah, that's all I wanted to show.
All right, let's send the speaker. All right, and finally, we'll have Jeremy, also from Cornell, to talk to us about build tool orchestration.
Hello, as new here? Uh, oh no, I don't think
Did
so.
you share your screen?
Yeah, yeah, give me a sec. Cool. I didn't see a green thing, so I wasn't sure if audio was working.
Yeah, we can hear you.
Display, okay, there we go.
All right.
This, is this big enough for everyone? Cool.
A little bit bigger might be nice.
All right, this good? All right,
All right.
cool. So I want to talk about FUD2, which it solves basically a problem that we had. So I guess this is for me and also Adrian. That solves a problem that we had when running this stuff in Calyx IR, which is just a big suite of tools to do compiler stuff for hardware. So basically what we had is we had a bunch of tools that we need to run, and it's really annoying to like write a bunch of scripts to do this. So what do we want? So we want something that is easy to run. So you can just kind of like run a single command for it. You can configure it and run more commands, but ideally you can just run one. Requires not that much setup, and it's easy to add support for other tools to it. So it's not like some initial tool that's like hard coded with like support into a bunch of different like specific like like vendor toolings or like the Calyx infrastructure itself. All right, so the things to notice about this are like, let's say you're writing like design flows. These are like big bash scripts. Often they'll like be split up into a bunch of smaller different scripts, and that's really nice. But what you can do is you can essentially say, okay, each of these scripts do some atomic thing. Let's give types to that thing. And if we add types to those things, then we can reuse them by just writing an algorithm to stitch all these typed little atomic scripts together. Okay, so that's really abstract. So let's show a demo of that. All right, so here we go. So what we have here is we've got this thing, which is example.fuse, which is a Dahlia program, which is just like some high-level language that we want to simulate. All right. So what we can do is, I'm just gonna like skip to like kind of the punchline, is we can just type this thing here, example.fuse -o sim.exe. And I don't have sim data right now, but it'll still generate the exe just with like nothing, but it'll be fine. I can just type FUD2 example.fuse -o sim.exe -set sim data equal to like nothing. And when I do this, it'll call out to the Dahlia compiler, it'll call out to Verilator, and yep, there's Verilator. And you can see we get here sim.exe generated. So, okay, that's basically what we're trying to do here. So how does this magic actually happen? Okay, so what's effectively going on here is if we actually run this with this mode thing here, so dash mode plan, we can see that it's calling these three different things. So these are essentially like the typed atomic design scripts that I mentioned earlier. You've got, or flip scripts that I mentioned earlier. You've got Dahlia to Calyx, Calyx to Verilog, and Verilator. So what Dahlia to Calyx does is it takes in some file representing a design Dahlia and outputs that design compiled down to Calyx. You've got Calyx to Verilog, which then takes that design in Calyx and lowers it down to Verilog. And then you've got Verilator, which takes that design in Verilog and creates like some executable to simulate it. Yeah, so at a high level, that's all it's doing. It's taking these different scripts, which have already been written, and it's automatically figuring out how to stitch them together. So I think that what's worthwhile doing is actually looking at one of these scripts. This is going to be the Calyx to Verilog script. I'm lying slightly, but because it's like slightly different, but this is like basically, this would work to replace the current one. So what you have here is these are the states. These are the types. So this represents like a Calyx file. This represents a Verilog file here, this Verilog state. And we can see here that we then define these things called ops, which translate these Calyx states into Verilog states. So this is what I mean. This right here is like the type signature. It takes something in the Calyx state and turns it into a Verilog state. It takes a Calyx file, lowers it down. And then we can see how does it actually do that? Well, it's basically just says, okay, we can just call a command. So what we have here is we define a function in this language, and this function takes some configurations from a TOML file that we have, and it just runs a shell command. So doing this, it's basically the same thing as if you were to write like a bash script for a flow like this, but it allows you to like reuse all of these different parts and type them so automatically you can find out pass through it. I think the final thing I want to show is like to give an example of why this seems useful. This is going to be very, very small, but making this a little bigger, you can see the reason why this is hard is because it's just to like impress why is this useful. Well, there's a lot of things that you want to do, and just having a bunch of scripts and like orchestrating them with like this many stuff is kind of difficult. So just being able to automatically like go through, run the correct stuff to go here, run Verilator and hit the sim is very nice. So that's basically how it works. That's the problem it solves. Cool. Yeah.
All right, let's thank the speaker. All right, so now we'll have the 20 minutes for small group discussion. Okay, all right, and I'll start off with a matrix question. So there was some discussion about the REPL approach, and specifically, can the REPL-driven approach expose performance bottlenecks beyond just correctness checking, state checking, and things like that? So I think there was some interest in that.
Performance as in like power performance area, next frequency.
I think I saw like latency, stalling, throughput.
Okay. So in my vision for this is working at a functional behavioral simulator level first. So you could collect it. I don't see why you couldn't. But the core part of this vision has really been more about debugging and correctness first, adding in the ability to collect those metrics as similar to the way you can install a watch expression GDB could be an interesting way to move forward, especially if you're directly interacting with it and you get like a print, you exceed some stall time, but I have not considered that yet.
I guess any questions from the room?
Hey, forgive me. I just.
Oh, sorry, just name and affiliation.
Steven Iser, Broccoli, just a tiny industry company, here for industry guys. Since there were no other questions, I decided to hop in. Forgive me, I slightly missed the session, but I did skim the paper and I noticed the mention of a Lisp-like approach, or at least taking this abstraction from Lisp dialects. And given the talk earlier on Haskell and functional programming abstractions, was there any natural way in which to maybe find some synergies between this lambda calculus dialects?
I don't see why not.
I just want to surface that
Yeah.
as a pattern.
I have been considering, especially because I'm approaching this from a Lisp world where make a DSL for everything. Sure, for sure. I don't see why not.
Thanks.
All right, so we'll go to another matrix question. Another theme that was discussed in matrix was how do hardware verification modalities scale with newer abstractions, new DSLs and HLS? So do traditional RTL level debugging workflows, do they remain viable when we introduce these new abstractions, or do they become a hindrance?
That, I think, is a two-pronged answer. Especially if you're coming from HLS, you already have interactive debugging tools available to you. HLS, very grossly, broadly construed, is pragmas on top of C and C++. So you can just run GDB on top of that compiled program and test it there. But at some point, that HLS will get turned into either Verilog or VHDL or system Verilog, what have you, at which point the debugger I'm considering and proposing kicks in, and you get the same kind of interactive feedback. And then as you go down, that would still mostly stay the same. Now, when you get to new HLS languages, things change. But I don't see, like, if you're still hitting Verilog at some point, you're still going to exhibit the same behavior that you would see when you hand wrote the Verilog anyways. And this new debugging system would be able to kick in.
If there are no questions from the room, I have a quick follow-up question to that, which is that, let's say if you're using some type of new DSL or HLS or abstraction and you run it in the abstraction simulation environment, it works great, and then you get the Verilog and it doesn't perform as you expect, how do you debug this type of situation?
So that immediately signals to me that there is a mismatch in the semantics between the two languages and how they're implemented. The same way you can have a semantic mismatch between Verilog and generated hardware in an FPGA. I had a bug that was impossible to reproduce in Verilator because Verilator has different execution semantics than an FPGA. So at that point, I don't know how much a tool can help you more than you being aware of what you're doing with the tool.
Got it. Any other questions from the room? Okay, if not, I will move to another matrix question.
Just for fun, I can
sorry.
vocalize one. I'm just
All right.
for the variety, I guess, but it's directed at Ethan and the Marlin framework, which is basically like seems great and has like shaves off a lot of the rough edges. If anyone's ever used CocoaTP, which is like also a high level way to write test benches. The question is essentially like, do you think everyone should move from CocoaTP right now? Are there like use cases that you don't think that Marlin covers that CocoaTP does? What's your pitch for what people should do? Or Ethan?
Was that addressed to me?
Yes.
Okay. I would argue that if you know Rust, then you can try out Marlin. And that would be the extent of my pitch. I think like if you know Rust, you can start using Marlin for your new projects. Um, I think the big nice thing about Marlin is that it does just work with newer HDLs. But the main thing that would help that, which is, for example, type translation of algebraic data types is not ready. So it may be a little rough to use it because then you're just using you will then be interfacing with, for example, a Verilog like interface. Um, but at least in my experience, it's a lot easier to do the kinds of things I would want in verification with Marlin than CocoaDB. And I think I saw, for example, Franz develop uh um he had a game with the VGA top, and he was able to develop the rendering in software with Marlin extremely quickly. So that gave me a lot of confidence that the approach is good.
All right, so another matrix question is, what are the trade-offs between interactive debugging and verification versus automated debugging verification? So, you know, which modalities like testing, debugging, formal verification, which ones can stay and which ones must evolve to allow us to iterate on hardware designs more rapidly?
I think all of those have a place, honestly. Automated testing and formal verification. So formal verification is great for proving that the thing is correct, that when you're building it. And as newer languages are working, as it is lowered through the compiler as well to make sure you did not break what you had formally proven earlier. Automated testing is great for running a huge corpora of test suites. But then interactive debugging, just like in software, is great for when one test out of 20,000 fails on one commit. You can drill in and figure out why that one failed. Or you want to prototype a different implementation of a core piece, like you're pipelining a module, for example, and you want to ensure that you are maintaining the same behavior across clock cycles or something like that. Having an interactive test to prove to yourself what you wrote is correct is where that would fit in, along with formal verification, and then a suite of automated tests behind it. So really trying to match what hardware does not have right now to what software has been doing for the past however many years.
I guess if there are no other questions, there's one kind of a bit to zoom out a little bit, a general question for both our panelists and the LATTE community as a whole. How do we kind of scale our new debugging methodologies, new tools, new abstractions to scale beyond toy designs? So can our new tools and our new innovations handle the state space and complexity of quote, quote, real hardware without becoming a performance bottleneck in itself?
Seems like maybe a Federico relevant question. You mind me calling on you?
Yeah, maybe I would say from a practical point of view, test with actual designs. So test your build tool or your debugging tool with actual designs as big as possible as you have.
Yes, I guess if I could jump in on that, I mean, the whole point of abstraction is really to solve that problem. It's so that you can do more simulation faster and get past the burden of all the detail that's in design. So if your methodology is approaching this problem right, abstraction is the solution to that problem, not an aggravant.
All right, I guess if nothing else, then let's thank the panelists again.
Sorry,
Oh, sorry, one more. Okay, all right.
I just wanted to raise, that was such a good question from the matrix, which is, somebody was asking, briefly referenced in his talk about, all this is sort of complicated when by the fact that you may have process specific concerns. It was like maybe the particular technology, or particular process that you're using, maybe that has like really big impacts on the architecture that you want. And it's just kind of hard to incorporate that stuff into early stage architectural level design. And I guess the question is sort of like, what should we do about that? Is it hopeless? Is there anything we can do about kind of like raising PD level stuff to the architecture layer?
I mean, I won't say there isn't hope. But at that point, you're being very targeted about what you're building. And this moves from, say, an exploration style of thing, where a style of design, to an engineering one where you need to fit within these physical constraints. And I feel like there has to be some amount of abstraction or language capabilities to be able to express that. But you're also fundamentally changing what the design is. So I will say there is space for it. I'm not sure what it would be beyond being able to have what we already have now, a golden reference model and a physical realization based on the PD you're working with.
All right, in that case, so on that note, let's thank the panelists again.